day, everyone. I am Naima Tidto from Group 8, and today we will be discussing Chapter 9, which is all about project scheduling, PERT, and CPM, alongside my group mates Alijam, Tago, and Princess Tomawis. So, let's start. In many situations, managers are responsible for planning, scheduling, and controlling projects that consist of numerous separate jobs or tasks performed by a variety of departments and individuals. Often, these projects are so large or complex that the manager cannot possibly remember all the information pertaining to the plan, schedule, and progress of the project. In these situations, the program and evaluation and review technique PERT and the critical path method CPM have proven to be extremely valuable. So it says here that managers in a business, company, or firm are the one always responsible for planning, scheduling, and controlling each project performed by different departments and individuals. Due to the large number of projects and its complexities, remembering all the necessary information about a certain project's plan, schedule, and progress is hard for the manager. So in this kind of situations, the managers use the PERT and CPM method. PERT and CPM can be used to plan, schedule, and control a wide variety of projects. Number 1, research and development of new products and processes. Through the use of PERT and CPM, the managers discovers new processes to best complete the project on time. Number 2, construction of plants, buildings, and highways. PERT and CPM is being used in construction projects as they are complex and large to manage. Number 3, maintenance of large and complex equipment. PERT and CPM helps the manager understand how various resources are being acquired, where they are being stored, and where they are being transported. Number 4, design and installation of new systems. So in this kind of projects, the project manager must coordinate all the activities to complete the project on time. PERT and CPM can help answer the following questions. Number 1, what is the total time to complete the project? Or how many weeks will it take to complete the project? Number 2, what are the scheduled start and finish dates for each specific activity? Number 3, which activities are critical and must be completed exactly as scheduled to keep the project on schedule? So PERT and CPM helps the managers identify the critical activities in a project. The critical activities in a project are the longest series of tasks as they take a lot of time, and if they are delayed, the entire project would also be delayed. Number 4, how long can non-critical activities be delayed before they cause an increase in the total project completion time? So when we say non-critical activities, they are the activities that can be pushed through their past due date or deadline without affecting the project due date as they are not critical. Project scheduling with known activity times. The owner of the Western Hills Shopping Center is planning to modernize and expand the current 32 business shopping center complex. The project is expected to provide room for 8 to 10 new businesses. Financing has been arranged through a private investor. All that remains is for the owner of the shopping center to plan, schedule, and complete the expansion project. Let us show how PERT and CPM can help. The first step in the PERT or CPM scheduling process is to develop a list of the activities that make up the project. Table 9.1 shows the list of activities for the Western Hills Shopping Center expansion project. Table 9.1 also shows the immediate predecessors and the activity time in weeks for each activity. So as you can see here in Table 9.1, in the first and second column, there are 9 activities labeled from activities A to I, while the third column is the immediate predecessor. Immediate predecessor identifies the activities that must be completed to enable workers to start or push through with the rest of the activities. So, activities A and B don't have any immediate predecessors as they are being presented in dash, so they can start as soon as the project starts. While activities C, D, and E's immediate predecessor is activity A, so they cannot be started unless activity A has been completed. Activity F cannot be started until activity E has been completed. Activity G cannot be started until both activities D and F has been completed, and so on. While the last column is the activity time, or the total time required to finish each activity. For example, activity A takes 5 weeks to complete, activity B takes 6 weeks, activity C takes 4 weeks, and so on. And if we add all the activity times from activities A to I, we get a sum of 51 weeks. In other words, the total time required to finish the project of providing rooms for 8 to 10 new businesses is 51 weeks. Using the immediate predecessor information in Table 9.1, we can construct a graphical representation of the project, or the project network. So, this is what a project network looks like. Figure 9.1 depicts the project network for Western Hills Shopping Center. Nodes represent activities using rectangles, and the arcs represent the precedent relationships through the use of lines with networks. So as you can see here in figure 9.1, the activities are written inside the rectangle or the nodes, while there are also arrows, lines with arrows, or the arcs that represent the precedent relationships. So for us to further explain figure 9.1, let's take a look at table 9.1. Activity C, D, and E's immediate predecessor is activity A, right? Which explains activity A's arrows pointing towards C, D, and E, as activity C, D, and E cannot be started until activity A has been completed. Same goes for activity F. Activity F's immediate predecessor is activity E, which means activity F cannot be started until activity E has been completed, and so on. This is applied to all the activities with immediate predecessors. So for us to further understand the project network, here is another simpler figure. In this figure, activity 2 is a successor of activity 1, and activity 1 is a predecessor of activity 2. In other words, we must complete activity 1 before we can finally proceed to activity 2. So now let's proceed to the critical path. Critical path. Critical path is used to determine the project completion time. Since all other activities or paths are shorter in duration, it won't matter. It won't affect or delay the project. A path is a sequence of connected nodes that leads from the start node to the finish node. So for example, in figure 9.2, there are 4 paths that leads from the start node to the finish node, which are the path A, E, F, G, I, path A, D, G, I, path A, C, H, I, and path B, H, I. If activities on the longest path are delayed, the entire project will also be delayed. Thus, the longest path, or the path that requires the most time, is the critical path. Activities on the critical path are referred to as the critical activities for the project. Determining the critical path. We begin by finding the earliest start time and the latest start time for all activities in the network. To get the earliest finish time, we will use the formula EF is equal to AS plus T. Let EF be the earliest finish time for an activity, ES earliest start time for an activity, and T activity time. So activities A and B can start as soon as the project starts, as it doesn't have any immediate predecessors, so we set the earliest time for activities A and B equal to 0. So with an activity time of 5 weeks, the earliest finish time for activity A using this formula is 5 weeks. We will write the earliest start and earliest finish time in the node to the right of the activity letter. Using activity A as an example, we have this. So now let's find out the earliest start time and earliest finish time for activities C and H. So for activity C, its immediate predecessor is activity A. So we will get the earliest finish time of 5 weeks as the earliest start time for activity C. Now if we add earliest start time 5 to the activity time 4, we will get the earliest finish time of 9 weeks. Now for activity H, with both activities B and C as its immediate predecessors. To get the earliest start time, we will select the earliest finish time's largest value. So if we can compare earliest finish time B6 and earliest finish time C9, we will select 9 as it is the largest value. Now if we add earliest start time 9 to the activity time 12, we will get the earliest finish time of 21 weeks. Continuing with this forward pass through the network, we can establish the earliest start times and the earliest finish times for all activities in the network. So, what we did earlier was a forward pass as we started from activity A and ended with activity I to find out the earliest start times and the earliest finish times for all of the activities in this project network. But now, we will be doing a backward pass, or we will be going backwards, starting from activity I and ending with activity A to find out the latest finish time and the latest start time for each activity. So to compute the latest start time, we must use this formula. LS is equal to LF minus T. Let LS be the latest start time for an activity, LF latest finish time for an activity, and T is the activity time. So the total completion time for the project is 26 weeks. So we will write it as the latest finish time for activity I minus the activity time 2. We will get the latest start time of 24. And the latest start time of activity I will be the latest finish time for activity G minus activity time 14 equals latest start time of 10 weeks. And this will be the latest finish time for activity F minus activity time 4 equals latest start time of 6 weeks, and so on. This is applied to all the paths in the network. Take note that in finding the latest start time, we must use this formula. After we complete the forward and backward passes, we can determine the amount of slack associated with each activity. Slack is the length of time an activity can be delayed without increasing the project completion time, or in other words, it is then also called the non-critical activities. The amount of slack for an activity is computed as follows. Slack is equal to latest start time minus earliest start time equals latest finish time minus earliest finish time. In general, the critical activities are the activities with zero slack, as they cannot be delayed even for just a week, as it will affect or delay the entire project. For example, the slack associated with activity C is latest start time minus earliest start time equals 8 minus 5 is 3 weeks. Hence, activity C can be delayed up to 3 weeks, and the entire project can still be completed in 26 weeks. In this sense, activity C is not critical to the completion of the entire project in 26 weeks.
Contributions of PERT and CPM. So every project manager must look for the procedures that will help them answer important questions regarding the planning, scheduling, and controlling of the project. So it means that managers are in control and they must have a procedure in creating the project. So the 4 questions that was mentioned earlier has been now answered. So the first one is how long will the project take to complete? So the answer to that is that the project can be completed in 26 weeks if all of the activity are completed in schedule. So the second one is what are the scheduled start and finish or completion times for each activity? So the answer to that is that, which can also be seen at the table 9.2, is that earliest start, earliest finish, and latest finish are shown for each activity. So number 3 is which activities are critical and must be completed exactly as scheduled to keep the project on schedule. So the answer to that is that activity A, E, F, G, and I are the critical activities. And then the last one is how long can non-critical activities be delayed before they cause an increase in the completion time for the project. So the answer to that is that 9.2 also shows the slack associated with each activity. Therefore, the program evaluation and review techniques and the critical paths methods are valuable in managing any project due to the procedure it gives. So larger projects usually requires greater efforts to develop the immediate predecessor relationship and the activity time estimates. This is due to the fact that larger project usually has more activity activities in order to complete those projects. So the procedure and contribution of the PRT and CPN to larger projects can be shown at the shopping center expansion project. So furthermore, computer packages can be used to carry out the steps of the PERT or CPM procedure. So these computer package are those softwares that can be used to provide the PERT and CPM procedure. Summary of the PERT CPM critical path procedure. So there are 9 steps total in creating the PERT and CPM procedure. So step 1 is to develop a list of the activities that makes up the project. Step 2 is determine the immediate predecessor for each activity in the project. Step 3 is to estimate the completion time for each activity. Step 4, draw a project network depicting the activities and immediate predecessor listed in Step 1 and Step 2. Step 5 is to use the project networks and the activity time estimates to determine the earliest start and the earliest finish time for each activity by making a forward pass through the network. The earliest finish time for the last activity in the project identifies the total time required to complete the project. Step 6 is to use the projection completion time identified in Step 5 as the latest finish time for the last activity and make a backward pass through the network to identify the latest start and latest finish time for each activity. Step 7 is to use the difference between the latest start time and the earliest start time for each activity to determine the slack for each activity. Step 8 is to find the activities with zero slack. These are the critical or the important activities. And last step is to use the information from Step 5 and 6 to develop the activity schedule for the project. Project scheduling with uncertain activity times. So it is a process of scheduling for a problem involving new product research and development, and it has generally none or little exact amount of data for each activity. So this is in line with the businesses that are creating new products in the market. So an example is the Dottery Portabac project. So the HS Dottery company has manufactured the industrial vacuum cleaning system for many years. But recently, the company have considered manufacturing a cordless vacuum cleaner. So the new product is called the Portavac. So the first step in the project scheduling process is to identify all of the activities that makes up the project and then determine the immediate predecessor for each activity. Once we develop the project network as seen in the figure 9.8, which is the Portavac cordless vacuum cleaner project network, we must now calculate the time required to complete each activity. Then the information will be used in a calculation of the total time required to complete the project and in the scheduling of specific activities. This can also be seen in table 9.3 or the activity list for the Portavac project. So, to incorporate uncertain activity times into the analysis, we need to obtain 3 time estimates for each activity. These are the optimistic time, most probable time, and pessimistic time. So, what do you mean by optimistic time, most probable time, and pessimistic time? So, optimistic time means that the activity time is progress ideally, while the most probable time is that the activity time under normal conditions, and then the pessimistic time is the activity time if significant delays are encountered. So using activity A as an example, we now see that the most probable time is 5 weeks with the range from 4 weeks into 4 weeks to 12 weeks. Here's the problem. If the activity was repeated a large number of times, what is the average time for that activity? So in order to get the average time for the activity, there is a certain formula that can be used. So time is equals to A, or most probable time, plus 4M. M stands for most probable time, and plus B, which is the pessimistic time divided by 6. So for activity A, we have an average or expected time of 6 weeks. Since our activity times is uncertain, we can use the variance to describe the dispersion or variation in the activity time values. So the formula of the variance can be get as variance is equals to open parenthesis B minus A divided by 6 close parenthesis raised to the power of 2. So therefore, the variance of activity A is 1.78, same as goes with other activities. Critical path. So after we get the project networks and the expected activity times, so the next step will be now the business will calculate the critical path that is important to know the expected time required in order to complete the project, and also determine the activity schedule. So when uncertain activity times are used, so the critical path shown are only the expected or average time to complete the project. The actual time required to complete the project may differ. The higher the variance, the more uncertain. After the critical activities and the expected time to complete the project had been determined, we can now analyze the effects of activity time variability, as shown in the figure 9.9 and table 9.5. So we can see that the expected time in weeks is total of 32 weeks. So now, proceeding with the forward pass through the network shown in the 9.10, we can establish the earliest start and the earliest finish times for each activity, which can also be seen at figure 9.11. It also shows the duration of the ES and EF of the project network. So the duration means the time required for its earliest start and earliest finish. So since the earliest finish time for the last activity is 17 weeks as shown in the figure 9.11, therefore the expected completion time for the Fortabac project is 17 weeks.
What is cost project scheduling uncertain time? Let's proceed to its formula, which is T denote the value of T, which is the sum of the expected times for the critical activity is. So the formula of it is E times T is equal to TA. Next will be the variance of the project time is the sum of the variances or two critical path activities to the variance for the Fortabac project completion time is. So the formula of it is that 0, 2 is equal to 0 to A over E plus 0 to A plus 0 to 1 or 0 to over 1. Okay, so the normal distribution of project completion item for the Fortabac problem. As you can see, the project scheduling PR or CPM and the future, which is the probability the Fortabac will meet the 20 weeks deadline to even through activity time variability can cause the completion to exceed 17 weeks. Calculation indicate the excellent change that the project will be completed before the 20 weeks. Now, The notes and comments is for project involving uncertain activity time. The probability that the project can be completed within a specific amount of time is helpful managerial information. However, remember that the probability better made is based only in the critical activity. When uncertain activity times exist longer than expected completion time for one or more non-critical activities may cause on original non-critical activity is become critical and hence increase in time required to complete the project. By the frequently monitoring the progress or the project to make sure all activities are on schedule. So the project manager will be better prepared to take corrective action if a non-critical activity being to lighten the duration of the project. Now in 9.7, and as you can see the original list for the 2 machine maintenance project, in 9.3, considering the cost item trade-offs, the original developers or CPM provide the project manager with the operation or adding resources to selected completion time, added resources such as more workers, overtime, and so on. Generally increase product cost or generally increase project cost. So the decision to reduce activity time most take care into contention the additional cost involved the effect. So the project manager take an decision that involves trading, reduces activity time for additional activity costs. So in 9.7, it defines a 2 machine maintenance project consisting 2 activities because management has had sustainability or let us say substantial with similar projects. So the time for maintenance activity are considered to be known hence and single time estimated is given for each activity. Next is the nomenclature for making critical path. Calculation for maintenance project network is the same on use to end the critical path in the network for both and western hills. Shorting center expense project and the Portovac project. Next is the table 9.8, the activity schedule for the 2 machine maintenance project. Now, suppose that current production level make completion and maintenance project with 10 days. Imperative by looking at the lesson or by looking at the length of the critical path of the network or 12 days, we realize that meeting the desired project completion time is impossible unless we can shorten selected activity time. Next, to determine how much activity time it needs information on how much each activity can be crushed and how much the crushing process cost. So this is the use of the three formula, which is the TI, T apostrophe I, and MI. So TI is expected time for activity I, and T apostrophe I time for activity time I under maximum crushing, and the MI maximum possible education in time for activity I due to crushing. So this cost KI for each activity is given by CI donate the cost of activity I under the normal of elected activity time, and CI donate the and C apostrophe I donate the cost of activity I under maximum crushing. Next, so if the normal expected time for activity A is 7 days, at the cost of CA will be $500, and the time under the maximum crushing in 4 days of C apostrophe A will cost $800. Equation natin is MA equals 7 days minus 4 days is equal to 3 days. So as you can see again, the table 9.9, the normal crush activity data for 2 machine maintenance project. These are the total cost, time, days, and other for project scheduling or for the machine maintenance project. So let me describe how linear programming can be used to solve the network crashing problem. The PRT or CPM, and we know that when the activity starts at the earliest start time then finish time. So for example, time is equal earliest start time plus activity time. So moving YA to the left side is XAU plus times 7 equal Y minus A, and the under of it is the XA plus YA is less than 7. The last one will be the 9.3, considering time cost trade-offs. If we follow the same approach that we use for activity A, constraint corresponding to the finish time for activity is expected time is equals 6 days. So thus determine the optimal crushing for each of the activity. We must solve a 10 variable to 12 constraint linear programming model. The linear programming solution from either Lingo or Solar provided the critical solution or crushing activity. So A by 1 day and activity E by 1 day, which the total crushing of $100 plus $250 is equal to $350, which the minimum cost crushing solution, the activity time are as follows.